Okay, so let's go back to where we were. If you remember, what I was in the middle of doing was proving to you that I gave you basically these descriptions of what deletion and contraction do for a vector configuration. And that's what I was going to prove. So I said V is some vector configuration. I guess I called it E, actually. In a vector space V, I said E was an element of the configuration, so one of the vectors, and so I defined two new configurations. The first configuration was the deletion, which were the vectors E minus E in V. So you take all the vectors except the one that you want to delete. And then the contraction. And for that, what we said is that you take these guys and project them onto the, take them mod E. In other words, if you prefer to think about it this way, you project them onto the octagonal or orthogonal complement. Okay. So pi is the orthogonal projection onto, I guess this isn't really E-perf, but the orthogonal complement to the span of E, which is going to be a line. Okay. And so I think I stated this, but I didn't prove it. That basically, if you take the matroids of these two configurations, then you get the deletion and the contraction of the matroid of this one. So the matroid on the deletion is just a matroid with E deleted. And so E is a vector configuration. E is one of the vectors. Basically, deletion and contraction deletion and contraction correspond exactly to these two procedures. Okay. So let's prove this. So first thing, let's show that an independent set here is an independent set here. So when is a set independent? And remember that the ground set of these matroids is E minus E in both cases. So let's take some subset of E minus E, some subset of the ground set. So when is I independent in the deletion? Well, remember that we said that we described the independent sets of the deletion of one element in a matroid. We said that if you take a matroid and delete one element, then the independent sets are the independent sets of the matroid that didn't contain that element. So if and only if I is independent, linearly independent, and it doesn't contain E. That's what it means to be an independent set in the deletion matroid. Okay. But the second condition is an empty condition, because we're assuming already that I is inside E minus E, so the element E is not in this matroid. This is an empty condition, and so this just means I linearly independent, which means I is independent in in this matrix. In other words, there's nothing to say here. I think it's basically linear independence here means linear independence here. There's nothing to say there. Okay. For the second one, you actually want to say something. So when is I independent in the contraction? Well, we said that in a matrix contraction, if you contract one element, then the independent sets are those such that when you take the union with E, that's independent in the matrix. And we said that this was assuming that E was not a loop. Okay. But so let me prove this for non-loops, and you guys can prove it for loops. So assume E is not a loop. If it is a loop, then it's easier. So if it's not a loop, then this is what this means. And now what this means is that you don't have linear dependence of the form something involving these guys. Okay, so I don't know, we can write it as C1 V1 up to CK VK, and you're allowed to include E. Okay? That's what it means. What does it mean for a set to be independent in the matroid of the projected configuration? So this E/E is the projected configuration. So I is independent if and only if the projected vectors are independent, linearly independent. In other words, you don't have an equation, no linear equation of the form C1 times the projection of V1 plus CK times the projection of VK equals 0. Okay. I should have said that V1 up to VK are I, right? And so projection of V1 up to projection of VK are the set of projections of I. Okay. Now, I want to show that these two things are equivalent. So basically what I want to show is that these two statements are equivalent. Well, if you had an equation like this one, what happens when you project? Each one of these guys becomes this guy, and the projection of V is 0. So an equation of this form implies an equation of this form just by the fact that projections are linear operations. Okay? What if you have an equation of this form? Okay? Suppose you have an equation of this form. That means that, again, pi is a linear operation, so you can rewrite this as saying that the projection of C1 V1 up to CK VK is equal to 0. Okay? But what things project to 0? Well, remember that we're projecting onto the orthogonal complement of E, and the only thing that, you basically have a line E, the hyperplane orthogonal to it, and the only things that project to 0 are multiples of E. Okay? So if this guy projects to 0, it's because it's in the kernel of the projection, which is the span of E. Okay? And therefore, I have an equation of this form. So that proves that these two statements are equivalent. Any questions about my proof? All right. So what have we done so far? We said, last time I showed you what deletion and contraction do to graphical matroids. We saw that they correspond to graph operations of deletion and contraction. This shows that if you do deletion and contraction to linear matroids, then you have operations on the vectors that you can do. And so the next natural question is what happens with transversal matroids? What happens when you delete and contract in a transversal matroid? So that's the next thing we're going to do. Let's talk about minors of transversal matroids. Okay. And what is the big question we want to answer? Well, I showed that any minor of a graphical matroid is graphical. I showed that any minor of a linear matroid is linear. Now the question is every minor of a transversal matroid transversal? Okay. So let's talk about deletion first. Okay. So remember, a transversal matroid is described by some bipartite graph. And I don't know if I want to pick a special one. I can just draw anything. Okay. We number these guys 1, 2, 3, 4. These guys A. Actually, I want to do it the other way. A, B, C, D. 1, 2, 3, 4, 5. And remember that the bases are, if you think of these as men and these as women, then the bases are the maximal sets of women that can marry at the same time. Maximal sets of women who can marry simultaneously. Now, let's say, for example, and this is a matroid. On this set, right? On 1, 2, 3, 4, 5. Now, what does it mean to delete? I don't know, let's delete 4. So deleting 4 from a transversal matroid. Remember, what does deletion mean? It means you're considering the bases that don't involve this element. You take the bases not involving 4. And one way of imagining this is just saying, 4 decided not to get married anymore. I don't know. So 4 is not interested in being married to any of these people anymore. 4 doesn't want to marry. And it's very easy to construct the graph title model that I simply delete the edges that allowed 4 to marry. So this just corresponds to deleting 4 from the bipartite graph. Okay. So what did I just prove? Proposition that if you delete some things from a transversal matroid, it's still transversal. Okay. Any deletion of a transversal matroid is transversal. Okay, so that's good. That's a start. The proof was just about as easy as the proofs we've seen for graphs or for vectors. And hopefully we can find a proof just as easy for contraction. Okay, so what does it mean to contract element 4? Well, remember that if we contract a single element from a matroid, what we're saying is that we're considering all the bases that do contain that element. Yeah? So these are the bases that do involve 4. Okay. In other words, what I'm saying is that 4 really demands that she's going to get married today. 4 must get married. And so now I want to model this situation in my graph. How can I make a graph that tells me that 4 has to get married? I don't know. What do you guys think? I mean, if 4 didn't get married, okay, you delete the edges, no problem.
Could make some of the men, or one of the men that, make one of the men who are going to not marry anyone else.
What if you break away the edge between
So what you're saying is, for example, like saying that maybe D is the guy that's going to marry her, and so I'm not going to allow D to marry 5 anymore.
Right.
But
So
there's
that's,
another possibility.
but then the question is that, right? So, you know, what if 4 didn't marry D? What if she married B? Then what I should have done is delete the edges that went from B to these guys. And then you might say, well, let's delete both. So let's just delete the edges from D and the edges from B. But that's not fair to B and D. I mean, you know, it doesn't mean that because one of them gets to marry 4, the other one doesn't get to marry anyone.
Wait, you're suggesting let's delete the edge from 5 to D and from 4 to B?
So what I'm saying is,
Wait, actually, we didn't say
That'll do it, right?
Yeah.
What if you delete the edge from 4 to B and 5 to D?
What if you merge B and D together? That guy, either if 4 marries D, then either 1 or 2 has to marry B.
Yeah.
If 4 marries B, then 5 has to marry D.
wait, so I totally missed what you guys were saying while I was drawing my graph. So,
The suggestion was
so first tell me what the construction is.
So we're
to delete 5 to D and then delete 4 to B.
so 4.
So
to
delete
4.
this
So that's one suggestion.
and
Yeah.
this?
I have a different suggestion.
No, no.
I have a suggestion of making B and D into
I think I missed your reasons for doing this while I was. So the motivation is what? That I guess you're forcing
4 to marry.
4 to marry this one, but then you cannot allow this one to marry this one. But the problem with that is that it's not symmetric, right? Because maybe 4 actually got married to this one, and then you would have to do the other operation. Okay. So this construction doesn't work because it breaks the symmetry. 4 should be allowed to marry any one of these 2 people, either B or D. So then what's your suggestion, Kim?
So my suggestion is that we merge B and D into the same.
You merge B and D.
Human.
That sounds a little bit like a graph contraction.
In that we say, and then we delete 4 completely from our picture. Because what I'm saying is, so let me follow my line of reasoning for a minute. If 4 marries D, then, right, if 4 marries D, then 5 has to, then B has to marry 1 or 2.
If 4 marries D, then B has to marry 1 or 2.
Right. If 4 marries B,
Uh-huh.
then D has to marry 5.
If 4 marries B, then D has to marry 5, right?
Right. So I'm sort of, in some way, I'm getting those guys, that if I take 4 out of the picture completely and move B and D into being the same character, then I've got either 1 or 2 gets married or 5 gets married to whoever this character is.
What you're saying is making perfect sense to me. The only problem is that it's wrong, but I don't know why.
It's okay.
But okay, so what is Kim saying? Kim is saying that I should leave the things not involving 4 alone. But now, for 4, I'm going to say
I'm going to send 4
just
off to the monastery.
4 disappears. Okay, and then B and D are going to be merged, and they become one guy, which is called BD, and 1, 2, or 5.
Should have the same basis. Right. It's not necessarily the same weddings, but the same basis.
Now, I see a couple of problems, possible problems, potential problems with this. I mean, I think it makes good sense. The problems that I see are, for example, what if there were more than 2? What if 4 had more than 2 people? And so now what you're doing is merging a bunch of different vertices onto this one.
Right.
Seems like it might be a little bit dangerous because...
Does seem right.
Actually, I guess that's the problem, really. I guess that's the problem because, for example, if 4 wanted to marry everyone,
Right.
yeah, and you did this operation, then what did you just do? You killed the graph, right? Well, you said, okay, 4 disappears. These guys are all merged into 1. And okay, so now this person can marry anyone, but it's not the same matrix. Right. So I guess maybe this works for when there's only 2 guys that want to marry 4, but it doesn't work for more. Okay. And I mean, the point is we could keep trying this, and the reason we fail is because this is not true. It's not true that a contraction. It's not true that a contraction of a transversal matrix is transversal. And this is not a proof, but we're gonna see a proof. I mean, I wanted you to try that to see why the things that you would try don't work. But now we're gonna see that what blocks us from working is that it's not true that contractions of transversals are transversal. So proposition. A contraction of a transversal matrix need not be
show something that's not
transversal. And this is a very good point. We have not seen in this class a single example of a matroid that is not transversal. Or if we have, we didn't notice. I haven't proved to you at any point in this class that a certain matroid is not transversal. I've proved to you that matroids are transversal, but I've never proved to you that matroids are not transversal. And so if I want to prove this theorem, the first thing I'm going to have to do is show you a non-transversal matroid. Right? I asked this question in the forum for you guys to see if they would help me, and Cesar from Bogota came to the rescue and gave me an example. I mean, I knew these examples exist, but I'm going to show you one of them. So I'm just going to show you a counterexample. So we're going to take... First, let's start with a graph. Okay? And the graph looks like this. And I'll call these, I don't know, A1. We call these A, B1, B2, C1, C2, D1, D2. And I'm going to consider the contraction of A. So when you contract A, what you get is this graph right here. B1, B2, C1, C2, D1, D2. These graphs define 2 graphical matroids. Okay. The matroid of this graph has a list of circuits. And what are the circuits here? B1, B2, C1, C2, D1, D2, and then A, any B, any C, any D. So A, B, I, C, J, D, K. These are the circuits. What are this? So now, I know that the matroid of this guy is the contraction of A. What are the circuits? Well, I still have B1, B2. I still have C1, C2. I still have D1, D2. But now A isn't anywhere to be seen, and the other ones are B, I, C, J, D, K. Okay. Yeah?
You lost me there. I see the two graphs, but what's on the lower left there, matroid of G, what's under there, C?
So these are the circuits.
Oh, the circuits?
So I should spell, let me call this matroid M. So I'm saying that the circuits of M are these. And then I'm saying that this collection over here equals the circuits of the contraction. Okay. So here I have a matroid, I have a contraction, and I claim that this one is transversal and this one is not transversal. So claim is that M is transversal, but M contraction A is not. Two things to show. Okay. So for the first one, I'm going to have to come up with a bipartite graph that has these properties. Now, what does it mean for B1, B2 to be a circuit? If you want to build a bipartite graph. So B1 and B2 have to be vertices. They have to be women. And what does it mean to have a circuit? It means, first of all, they're not loops. So B1 and B2 can marry, but they cannot marry simultaneously. So what that means is that they must be only willing to marry the same person. That's why they're a circuit. One of them can get married, but not both. And that must happen with C1 and C2. And that must happen with D1 and D2. So far, so good. And now I need a circuit A, B, I, C, J, D, K. So what I'm saying is that I need a new woman such that you cannot marry this woman, one of these, and one of these. Okay? One way of accomplishing that is to let A marry any of these people. Okay? In that case, you know that you can only marry 3 of the women because there's only 3 men available, and therefore anything of size 4 cannot get married. Okay? And so this is our representation of this matroid, which shows that this matroid is transversal. So that's one. Now, to show you that this is not transversal, I'm going to start building a representation and showing you that I can't do it. If this one were transversal, then again, B1, B2, C1, C2, and D1, D2 are circuits. And so I'm forced to do this. Okay. Now, why are these 3 different? I mean, it's clear that B1 and B2 only want to marry the same guy. C1 and C2 also. D1 and D2 also. How do I know that these 3 guys are different?
Because if they weren't, then you'd
If-
have a bigger circuit.
Right, so if these C1 and C2 wanted to marry this guy, then I would have more circuits. Like B1, C1, so on.
Or
So
if they all wanted to marry the same guy, you would just get one bigger circuit, wouldn't you?
If they wanted
You
to-
No, actually I get smaller circuits. So if it was like this, then B1,
Oh,
no. If it was like this, then B1, C1 would be a circuit.
Oh, I see, yeah.
And B1,
Yeah,
B2, C1 would be a bigger
So you get a
dependence.
bunch of circuits.
But this is not the case, so
Yeah.
it must be like this, and these 3 men are different. And what that means is that B1, C1, and D1 can get married. But according to this guy, they cannot. This shows that B, I, C, J, D, K are independent, contradicting the fact that they were supposed to be circuits. So here's the proof. Here's the first proof that we have seen that a matroid is not transversal. Okay. And it's a little unfortunate, maybe, that transversals don't have this nice property that graphicals and linears have. Okay. But at least now we know. Now we know that when we take a minor of a transversal, the answer might not be a transversal matrix. So let me summarize what we know so far. So we know that graphical matroids are closed under deletion. They're closed under minors. So if you take any minor, you get a graphical matroid back. And remember, I lied in my notes. That's all you know. They're not closed under taken duals, right? In your homework, you proved that a certain graphical matroid, the matroid of K5, does not have a dual which is graphical. Linear matroids are closed under minor zones. And in fact, we showed that also they are closed under duals. The dual of a linear guy is linear. Okay? And we would have liked to put a third entry here that said transversal matroids are something, but that's not true. Okay? But so for the rest of the class, what I want to do is find what statement I should be putting here. Okay? It shouldn't be transversal matroids are closed, because that's a lie. So what am I going to put there? Well, what I want to do is enlarge the class of transversal matroids into something larger that is closed under minors. In other words, here I have the transversal matroids. Okay. I put them all in a bag. Now I can take deletions or contractions. What happens when I take deletions? Well, I still get transversal matroids. What happens when I take contractions? I don't necessarily get transversal matroids. I get something that I don't know what it is. Okay. Now, are transversal matroids contained here? In other words, is every transversal matroid a contraction of a transversal matroid? Well, sure, because if you take a matroid and you contract the empty set, you get the matroid. So this class contains transversal matroids. Okay. So maybe this is the class that I want. It's a bigger class, and it contains transversal matrix. The question is, if I take something in this class and I delete or contract, do I stay in that class? Well, let's see that, but we're going to give a name to these guys. So definition. This is what I told you last time is a gamoid. Gamoid is a restriction, contraction of a transversal matroid. Okay, so in other words, the name for these guys is gamoids. Okay, and what I want to ask myself is whether this is the class that I want to put over there. In other words, are deletions of gamoids gamoids, are contractions of gamoids gamoids. Well, let's M be a gamoid.
Is there any kind of matroid that's not going to preserve that structure under deletion? Seems like
We'll see one in just a second. So Jameson's question is, are there nice classes of matroids that are not closed under deletion? We'll see one in a second. Start with a gamoid. Okay. Actually, I'm not done with this picture, so maybe I'll start over here. Start with a gamoid. And that means that M is a transversal with something contracted. Okay. What is a contraction of this guy? What happens when you take your matroid and you contract something?
you still just
Well,
contracted A
M
and B.
is by definition T contracted A, and then you contract B, but then contraction has this nice property that it's commutative. And so this is just a contraction of T. So any contraction of a gamoid is a gamoid. Okay. What about a deletion? It's not deletion. If you delete B, then by definition, M is T contracted A. And then you delete B. Is this a gamoid?
Yeah.
Well, what you have to do now is remember that, again, deletion and contraction commute. So I can write this as T delete B contract A. And now I can say, well, here I have a transversal and I deleted something. But we know that deletions of transversal are transversals. And so what I have here is a transversal contracted something. So this is a gamoid. So this is the class that I want to put over here. Gamoids are closed under minors. Okay. But then that immediately raises a question. Which is, should I put a knot there, or should I not put a knot there? Are gamoids closed under taking duals? Well, by the space, you might think that I should put not.
I think not because of the homework.
It's not part of the homework, is it?
You have a problem on there that gives a reason to believe
That it would be not?
it doesn't prove it.
Well, the reason that I wanted to leave space here is because transversal matroids relate very nicely to another kind of matroid that we know by taking duals, which is really what we're wondering about here. So what happens when you take a dual here? We know that when we take the duals of the transversal matroids, we get exactly these guys called co-transversal matroids. This is an if and only if. You can go back and forth.
Do people talk about co-graphic?
People talk about co-graphic, sure.
Did we say that in here already?
I don't know if I have used the word in class, but co-graphic means dual of a graphic matroid. Co-transversal means dual of a transversal matroid. Now, if gamoids were to be closed under duality, then they have to contain co-transversal matroids. Because gamoids contain transversal matroids. When you take a dual of a transversal matrix, you're taking the dual of a gamoid. So this guy should be a gamoid. Okay. If that were true, then also if you start taking deletions and contractions here, you should still be getting gamoids. We don't know what these classes are. We know something about this class. Do you remember we showed something about deletions of cotransversal matrices? So the first thing that I wanted you to remember is that duals of transversal are dual with the cotransversal. We said that was the first relationship between transversals and cotransversals. But we proved a second relationship between transversals and cotransversals. What we said is that every transversal can be seen as a restriction of a cotransversal. If you remember, the way we did that is we said you start with a transversal is given by a picture like this. So this is a transversal matrix, and we said, well, what you can do is make a directed graph out of this by just sending everything in this direction. Okay. Call these guys B0. Okay. And consider the cotransversal matroid. The cotransversal matroid are the guys that can match, that can be routed to these guys. Okay. Now, if we delete B0, then what we get are the sets here that you can route to these guys, but the sets here that you can route here are precisely the matchings. Okay. If you go from here to here, then our routing is a matching. Okay. And so we said if you take this picture and you delete these guys, what you get is the transversal matroid you started with. So the transversal matroids are deletions of cotransversals. So transversals are contained in the deletions of the cotransversals. So we don't know much about this class, but we do know that the transversals are in here. Okay.
But don't we also, do we know that by that same construction that no transversal is a cotransversal? Is that following?
We don't know that, and actually there are transversals which are cotransversals, and we.
No, I meant no cotransversal is actually a. Wait, what am I? Because you need that B, your B naught set there. So if you didn't delete it, then.
So
a problem.
in this picture,
Yeah.
to this picture you can associate a transversal matrix and a cotransversal matrix, and they're never the same.
Yeah.
Because these guys are in the ground set of the cotransversal matrix, and they're not in the ground set of the transversal matrix. But there are transversal matrices which are cotransversal. Okay. So the more you stare at this, the more confusing it should be. I mean, now, for example, I said that there are transversals which are not cotransversal, which shows you that this is the class you were asking about, James. You have cotransversal matrices whose deletion are not cotransversals. Okay? And this is a big fat mess, but the point that I want to make is that I can go like this and say gamoids. In other words, what I'm going to prove to you is that this is a yes.
Okay. So why don't we do something similar then with graphs? Why don't we call the set of all graphs and co-graph matroids some name? And
You can. And you would have to think of an ugly word for it too. It's crucial in matroid theory to come up with bad words for things.
What's wrong with
Graphoid.
graphoid?
The problem with graphoid is that someone took that already. And they took semi-graphoid also. Just about every bad word is taken. It's not easy. Proposition. This is a yes. So the dual of a gamoid is a gamoid. And I think the problem when you do this with graphs is that this is not going to...
That still doesn't happen?
I'm not sure. It's a good question for the forum. To try to do this for graphical matrix. Let's prove that a dual of a gamoid is a gamoid. Okay? So, start with a gamoid. That means that it is a contraction of a transversal. Okay. T is transversal. So any transversal is a deletion of a cotransversal. This is one of these formal proofs where I'm just going to do things and just pull off a proof without ever doing anything. A transversal is a deletion of a cotransversal. U is a cotransversal. Okay. Therefore, M is U delete C contract B. A deletion of a contraction of a cotransversal. Okay. Take duals. This is the matrix we're interested in, the dual. So what I'm doing is taking this, this, and dual. Okay. Well, hopefully you guys did this problem in your homework already, where you showed that taking duals just reverses deletion and contraction. So this is exactly the same thing as dual delete C contract B. This is how dual and transversal, this is how duals and minors interact with each other, is that duals make contractions into deletions, deletions into contractions. Okay. Now what? What can you tell me about U star? Well, U is cotransversal, and so U star is transversal. Okay. Now, so this guy is transversal. Now let me just reverse the deletion and the contraction, which I'm allowed to do. And so what do I have here? I have a deletion of a transversal. And we showed that deletions of transversals are transversals. Okay. So what did I just pull off? M star is a contraction of a transversal, which by definition is a gamoid. Period. What did I do? This is just one of these formal arguments that, you know.
That means that your definition.
That means that this is probably going to work for graphs, actually. I never really used. I mean, what I used is those two statements over there, and there's some formal nonsense to pull it off. But I never told you if I give you a gamoid, how do you construct the dual? Well,
also,
I guess what you do is you just do all of this stuff.
All that
Snake through this stuff.
means to me is that gamoid is, the definition of a gamoid is a good definition to have.
Yeah, so I agree. This wouldn't deserve a name if they were just contractions of a transversal. And probably you were wondering why I bothered saying this word at all. And this is the reason, actually. The reason is that gamoids are this whole picture in one. Okay. In other words, actually, What I want to say is that gamoids are closed-under minors, and in fact, they are they're the smallest class with that property containing transversals. And why is that true? Because I started with a transversal and I took a contraction that has to be in there. So they are also the smallest such class containing transversals. Okay. And now that you have this argument at hand, you can, for example, we showed that every transversal is a deletion of a cotransversal. You can dualize that statement, and you're going to get that cotransversals are all contractions of transversals. We showed that the deletion of a transversal doesn't have to be transversal. The dual of that statement is that a contraction of a cotransversal doesn't have to be a cotransversal. So all of these statements and all of the ways that these classes are related to each other are implicit in this world of gamoids. Okay, that's it. And I want to make sure everybody knows that my office hours changed with daylight savings time, and now they're right after class. And I think that works for everybody. Is that what you guys told me? Almost everybody? So if it doesn't work for you, then I guess come for the old office hours, and that should work too.